Welcome to this lecture series on wireless and mobile communication. In this lecture, I'll cover some practical handoff scenarios. Thereafter, I will discuss on cells splitting, cell sectoring, and microcell joining concept. In practical handoff scenarios, we will take three different scenarios. In first case, we will consider mobile user with different speeds, then cell dragging problem, then inter-system handoff. If we see the figure where a cell is split into small cells, the small cells are served by the base stations which has low height and low transmit power, and they are taking care of the users which have low speed. And the big antenna which is centered at the located at the middle, it has a big height and its transmit power is high. It takes care of the high speed users. Now the question may raise, why the small base stations are not taking care of the high speed users? If these small base stations takes care of the high speed users, then there may be, since the speed is high of the users, within a given period of time the user may cross multiple cells and ask for multiple times handoffs. So that may be a burden for the system. So to avoid all this, low speed users are taken care of by the small cells and high speed user are taken care of this the antenna with the big height and high transmit power which is located at the center of the cell, and this is called umbrella cell approach. So umbrella cell approach is basically taking care of the users with different speeds. Next one is cell dragging, in which we can, if we look at the figure, in which that MS already moved from base station 1 area to base station 2 area. Since it has a strong line of sight with the base station 1, still it receives a very good quality of power, high power, which is greater than the handoff threshold. So it won't ask for handoff. At the same time, since it is in the territory of the base station 2, it will face a high, it will experience a lot of experiences, and which is not acceptable. This is called cell dragging problem. Another kind of handoff scenario where the mobile user is moving from one MSC area to the another MSC area. So if one user is leaving the coverage area of one MSC and is entering the area of another MSC, then the call might be lost if there is no handoff. Such type of handoff is known as inter-system handoff, and in order to facilitate this, mobiles usually have roaming facilities. So this is basically inter-system handoff. Now, so already I talked about a handoff process. What is handoff process? Type of handoffs in the previous lecture, and different generation wise how much the time, how the handoff time is reduced different generation wise, and that handoff threshold also. Now we are in 5G. Almost this handoff process takes almost near to 0 millisecond. Now we move to another aspects of the cellular communications. Now our aim is to improve the cellular capacity as well as improve the received SIR, because received SIR is a key factor for performance of the cellular system. If the SIR is good, then the performance of the network will be good. There will be less call drop, the quality of service will be high. So that's what now we'll take cell splitting, cell sectoring, and microcell joining concept, we'll learn the techniques one by one and their drawbacks and how to overcome. I'll discuss one by one. Cell splitting is basically, if we split the cells, then it will helps to increase the capacity of the system, but at the same time it will increase the handoff. Similarly, if we sectoring the cell, it will improve the SIR of the system, but it will also increase the handoffs, number of handoffs. So both the cases, handoffs are increased and it's a burden to the system. In microcell joining concept, we'll see there is no, it's a handoff free system. In cell splitting, the existing cells is divided to smaller cell. So if you look at the figure, basically here it's a 7-cell cluster. This cluster consists of 7 cells, and each cell consists of different frequency bands, so they are denoted by different colors. Now in the second figure, that cells are splitted into small cell and smaller cells, means okay. So cell splitting is a process of subdividing a congested cell into smaller cell such that each smaller cell has its own base stations with reduced antenna height and reduced transmit power. It increases the capacity of a cellular system since number of times channels are reused. So already I discussed in the first lecture that if you increase the if you replicate the more number of clusters, means if you increase the number of reuse of the frequency, then we can increase the capacity of the system. The same thing is happening here. Now, what are the different cells? If we split the cells, what kind of different cells are there? If we start from the bottom, it's a femto cell, 10 meter. It's like just a home. The radius of the cell is 10 meter. For a pico cell, it is 4 to 200 meter. The radius of the cell, you can say, is a big office or small campuses. Then microcellular, 200 to 2 kilometer, a small area with a 2 kilometer radius, that is a microcell. And macro cells means 1 to 30 kilometer. It's a basically, you can consider a small town or town area. These are the different kinds of cells according to the applications and use. The service provider creates the cells and provides the services. Now in cell splitting, that D by R ratio is kept constant. Why? The reason is here, since the cells are splitted, the D, that is a co-channel reuse distance, reduces. How we can come to know? If you see the previous figure, if you see here, see, better I go to the one or two more cells. Just a minute. Yeah. See, this A and this A, these are co-channel cells, so they can interfere each other. So you can look at the distance D between it. Now you can, if you see here, once it is splitted, you can look at here. Look at here. Now the center cell is splitted. Now again the frequencies are allocated. Now the distance, if I this red one also will also be splitted, but now for the simplicity, see, I'm taking this entire red region, that is entire cell is operating with the same red one, and this one is the red. So now you can feel the D is reduced. Similarly, R is also reduced since the cells are splitted. So that's what that D by R ratio remains or kept constant. Now what are the drawbacks of cell splitting? First of all, since the number of cells increased, obviously the handoff will increase once the user is moving from one place to the other place. And since the number of cells increases, so the cost of the system will increase, because you have to install more number of base stations, more number of antennas are there. So these are the drawback. So obviously it is if you want to get something, you have to pay for it. The same thing is here. We are achieving the higher capacity. We are splitting the cells. We are reusing the frequency more number of times. We are increasing the capacity of the system. So we are paying in terms of more number of handoffs and system cost. We'll take a problem to understand this cell splitting concept, how it affects our system performance. So the problem 6, if a cell of a radius r is splitted to create new cells and the radius of new cells is reduced by half, that is r by 2, what is the required transmit power for these new cells to keep the receive power same as the old cell for n is equal to 3? Means basically here one cell is splitted a number of cells. Now the cell radiuses are r by 2. It was previously, before splitting, it was r, and the path loss exponent of this region or of this area is 3. What would be the transmit power after splitting the cell for the new cells, keeping in mind that receive power for both the cases before splitting or after splitting is same? Why it is expecting same? Because to keep the quality of the service same. How we can do? So the relations, already I discussed this relation. The receive power is proportional to distance to the power n, that is minus n, where n is the path losses. The same relation is used here. PR old means that receive power old, that is transmit power old to the power r to the power n, and receive power new is PT new, new transmit power into r by 2 to the power of minus n, because we have considered the users are at the cell edge, on the cell edge, and base stations are placed on the in the center of the cells. So PR old is the new old receive power, PR new is the new receive power, PT old is the old transmit power for before splitting, the transmit power, and after split transmit power is PT new. So if we compare these two, means since it is told that new receive power and old receive power is same, so I'll get this relations PT new by PT old is equal to 2 to the power n. If you make the ratio, you will get it. It's a simple mathematics. So PT new is equal to PT old to the power by 2 to the power of n. So if I take try to find a dV scale, it would be PT new in dV, PT old in dV minus 10 log. If since it is told n is equal to 3, so it will be 10 log 10 base 8 and approximately 9 dB. So now once it is splitted, you have that system has to a base station of the small or splitted cells, the transmitter power of that base stations should be 9 dB less compared to the old transmit power. So that's what PT new should be, PT old minus 9 dB. This is a new problem. This is an exercise where suppose a congested area has 5 cells, and this is 5 cells for a cluster is not possible. Just for a sake of problem, it is given. Each cell consists of, it may be 7 or 4. Each cell consists of 80 channels. Find the total number of channels or capacity of the system. After splitting, if the same area, if it is covered by 25 smaller cells, find the new capacity. So it's a simple question. This is for exercise. Do your own. The next lecture, I will tell the solutions. Now come to the point, cell sectoring. The cell sectoring, in cell sectoring, the base station is located at the center of the cell or at the edge of the cell. It can be placed. Later on we'll see. Cell size is kept same. There is no cell splitting. the cell size is kept same. A number of directional antennas are used at the base stations. uh, if you see the figure, these are the basically different multiple antennas. So since there are three total 360 angles, so each antenna is serving 120 degree. So number of directional antennas depends on the number of sectors. So how many sectors I need, depending on that we will have to place the number of antennas. It reduces the co-channel interface and increases SIR. Sectoring of cells may be 60 degree, maybe 90 degree, maybe 120 degree, but here D by R ratio reduces. Why D by R ratio reduces? Because since we are sectoring, the D is changing here, but since there is no cell splitting, R remains same. So since D is reducing and R is remains constant, the D by R ratio reduces. So directional antennas power is transmitted in a single desired direction. What is directional antenna? What is the function? It is told here. Directional antennas power is transmitted in single desired directions, decreasing number of interfering co-channels, cells and co-channel interferences. Now look at here different sectoring. The first one case is the omnidirectional antenna. Second one is 3 sector. So each sector is 120 degree, where we have seen this these base stations consist of 3. So it's example of this 3 sector. That sectors may be, the 3 sectors may be this way, or you can place this is a 4 sector, this is a 6 sector. What are the drawback? Placing of directional transmitters at corners where these 3 adjacent cells are made. Okay, one is placement, finding the exact place where 3 different cells, because I told you can place it at the center, at the same time you can place this location is very difficult to adjust. So if there is any mismatch, there may be sectors may interfere to each other. So placing of directional transmitters at corners where 3 adjacent cells meet. Okay, because each sector, after sectoring, each sector will act as a one cell. Again here handoff will increase. Handoff requires while MS moves from one sector to another sector. This is the drawback also in cell sectoring. So here it is mentioned, if we sectored it, so it will be allocated 3 different sectors, 3 different cells. Now once we introduce the cell sector, the SIR equation now modified. Initially this QS was not there. It was S by I 1 by 6 under root of 3n whole to the power of n for the without sectoring. But once the sectors are introduced, then another term case have to multiply with the that existing SIR expression. Now the new equation with the cell sectoring for SIR becomes S by I is equal to Ks into 1 by 6 under root of 3n whole to the power of n. There is a one exercise, already we have done number of problems to calculate the cluster size for given SIR. This exercise is left for you. A cellular service provider decides to use a TDMS scheme that can tolerate SIR of 16 dB in worst case for n is equal to 4. The path loss exponent is given 4. Find the cluster size in the case of omnidirectional antenna. Omnidirectional antenna means that it is not sectored. 120 in this case, this one omnidirectional. Second, 120 degree sectoring means 360 by 123 sectors are there. So from there you have to find that case. 60 degree sectoring, that is when 6 antennas, 6 sectors are there, 6 directional antennas you have to place on the base station. Next you have to give your inference out of 120 sectoring and 60 degree sectoring, which one is better. So this is left for your exercise. I will take this problem in the next lecture and I will discuss this problem, discuss the solution as well as the inference. Now, microcell joining concept. Here if you see the microcell zoning concept, we can see that this area is basically covered by three different antennas. These three different antennas connected to the same base station through a zone selector. So obviously once this MS is moving from this area to this area, so it will be served, initially it will be served by this antenna. When it moves to this area, it will be served by this antenna. If you look at this change of channels or data sessions will be done through the zone selector, but there is only one base station is involved. There is no two base stations. Basically handoff is taking place between two base stations. So even if the user is moving from one base station to the another base stations, one area to the another area, there is no change of base station, so there is no handoff. So it's a handoff free concept. Okay, so today we learned about three different strategies, that is cell splitting for increasing the capacity of the system, cell sectoring to improve the SIR of the system, and microcell zoning concept to reduce the handoff. That's all for today. Next lecture I'll discuss the solutions of the given exercise problems along with the